As an epilogue for the lecture, I wanted to have one final video where I give my view on where you could go next if you're interested to continue in algebraic geometry. And so I just wanted to present a bit the different areas, the different kinds of things that you can continue to study, and a bit how they fit into what we did so far. And so the first step, if you want to continue, is to learn a bit more about the basics of algebraic geometry. And the very basics that we had a bit, but maybe not as much as you would need later, is to just study, for example, category theory. So this involves things like not only studying the categories themselves, but also new constructions there, like limits and co-limits. Then you can study more what are these functors between categories, define adjoint functors. Maybe you have already seen notions like abelian categories, and also make a bit more precise. I mean, we have seen in a lot of cases it was very useful to have to define objects in terms of universal properties, and we basically just did this by hand in each case, and just wrote down this property, but this can be put in a much more general framework. And so if you want to really study modern treatments of algebraic geometry, then having this category theory background is really very, very important. And I would say in this course, we did exactly as much as we needed, but not more. And this means that the basics are still a bit kind of selective or a bit fragmented. So this is something you could brush up on. And then there's kind of two different in the basics of algebraic geometry. There's two separate directions where you can continue. The one is the properties of both the schemes and morphisms between them. So we have seen a bit in this direction. So for example, we have seen what does it mean for a scheme to be reduced? What does it mean to be finite type over K and so on? But there's a lot more of these properties that you would need for more advanced things, like, for example, properties of schemes saying that they are basically nice, at least locally. So, for example, this would be act as normal, regular, or smooth. And then if you have morphisms between schemes, they can also have nice properties. This would be, for example, flat, proper, integral, and so on. For each of them, typically there is a commutative algebra concept behind it, and you would define the morphism having this property often by saying that if you choose some cover by affine schemes, then the corresponding maps of rings have this property. And so this direction looks a lot like going through the various properties of rings, making them into a geometric property of a morphism of schemes. And this would explain some parts of the commutative algebra course, which we maybe haven't seen so much yet. On the other hand, you can learn more about these quasi-coherent sheaves we have seen, and then also about this variant which we mentioned, the coherent sheaves. This covers this entire theory of locally free sheaves, which become these kind of line bundles and vector bundles over the scheme, like learning how do you really go from the locally free sheaf to this geometric incarnation of this line bundle and vector bundle. You could also take a kind of completion of this, making it not just having vector spaces as the fibers, but also having projective spaces as the fibers. So this would become projective bundles, and then define not just what is a projective variety, but what does it mean for a morphism between two schemes being projective. And then finally, an important characterization of there's a relationship between line bundles on a suitably nice scheme and so-called divisors, which are basically sums of codimension 1 subschemes. And so this would go more in this direction of the sheaves that we have seen. And then all of these three topics come together in an area called sheaf cohomology, which is the final chapter of the script by Gutmann, which we didn't cover. This sheaf cohomology takes a sheaf on a scheme X and associates to it some nice groups. And these are these sheaf cohomology groups denoted like this. And they are extremely useful because the data of a sheaf is just a very fundamentally complicated object. It has all these kinds of sections and all the open sets, and it's hard to control them. And these sheaf cohomology groups, it turns out, are pretty simple. They're often finite dimensional over the field that you work over, maybe, and they still retain a lot of information about the sheaf, and you can use this to study both the space X itself and then also the sheaf one. And when defining them, you would naturally start using language of derived functors, which comes more from this category theory. So somehow all this basic stuff kind of culminates in this sheaf cohomology. The reason why we didn't cover it in this course is kind of the course stops afterwards. And in a certain sense, this is a pretty technical thing to work through. So you have to basically have a lot of constructions, a lot of different well-definedness properties, and then we wouldn't really have applied it to anything. And I found this a bit kind of unsatisfactory. So it's important, but you wouldn't have gotten the payback of the payoff for working through this. So that's why we didn't really go in this direction. And so once you have unlocked this, and of course also still knowing the rest of the parts, there's a whole set of further directions in which you can go, which I would classify more as applications of the theory. So two central ones, which I'm not going to talk about so much, is you can go in this direction of number theory and so-called arithmetic geometry. And there the idea is you start studying equations over maybe the integers, or trying to solve these systems of equations, not over an algebraically closed field as we have done it for the majority of the course, but for example, try to solve equations over finite fields or over the integers, over number fields, and so on. So I won't say so much about this, but this is again an area which needs all of these prerequisites. And if you're interested in kind of number theory questions, it's certainly not wasted time to learn this stuff. And then there's other interesting directions, and I will just sketch a bit of this, which goes in the direction also of my own research, maybe. So if you are interested more in this differential geometry perspective, then you can consider learning a bit more about Hodge theory. So there the idea is that if X is a variety of the complex numbers, and for example, it's smooth, then its complex points are complex manifold. And then you have more this kind of complex geometry and differential geometry to play around with. And in Hodge theory, you basically try to understand this relationship between the differential geometry of these complex points and what does this have to do with the underlying variety. And what we have seen in the last time, namely that you can calculate the genus of a curve from its arithmetic genus, from a purely like just a number of linearly independent sections of the cotangent sheaf. This is kind of baby first example in this direction. Then certainly the study of curves is a big part of algebraic geometry, simply because curves are kind of the easiest non-trivial example of varieties. And so it's an example where you can actually understand very, very much about their geometry and about various things. So if you go in this direction, you would, for example, learn about the Riemann-Roch theorem, which tells you more generally, if you have a sheaf on a curve, how many sections does it have? How can you calculate this number? And also, we have seen this invariant, the genus of a curve, and then it's actually possible to classify for low genus, so genus 1, 0, 1, 2, 3, and so on. You can classify all of these curves. So basically write down what are all possible isomorphism classes. And this already goes in direction of the next box, which are moduli spaces. So these are basically, we have seen some examples of these, like the Grassmannians, the projective spaces, and so on. And so these classify some geometric objects. So for example, you could classify curves up to isomorphisms. And you can also classify certain types of surfaces, going up a bit in dimension. You can classify, given a fixed scheme X, you can try to classify what are all subschemes, closed subschemes of this. When you have an algebraic group acting on an algebraic variety, these are some of the notions which we have seen in the presence sheet. Then you can try to understand what is the quotient of this action, how can you classify group orbits, and so on. So this goes in this direction here, and then on the other side, you can also look a bit at what we saw, for example, with Bézout's theorem. So this is kind of flagship theorem of an area called intersection theory. So in Bézout's theorem, if you recall, it said that if you have plane curves inside P2 of degrees D and E, and they don't share a common component, then they have exactly D times E intersection points counted with multiplicity. And so trying to generalize this, so if you don't just have ambient space P2, if you have an arbitrary, let's say, variety X, then you would like to understand how do subschemes of X intersect. And for this, you would introduce an algebraic version of homology of X, such that the subschemes give you elements of these homology groups. And then intersecting them physically, like in Bézout's theorem, should correspond to some product operation on these homology groups. And then there will be a lot of connections to other things, like, for example, this Riemann-Roch theorem. On this side, you will then see it's just a very special case of more general things called the Grothendieck-Riemann-Roch theorem on the other side. And then finally, kind of these two areas, trying to understand moduli spaces which classify, for example, certain curves, and this intersection theory, this can then be combined to study a bit in this direction of enumerative geometry. So in enumerative geometry, you're trying to enumerate geometric objects. So you try to count, for example, how many curves are there on a given variety, satisfying some extra equations. And then the idea how these two arrows come together is, well, you first write down the moduli space of all possible curves on your variety. This comes from this direction, from the left. And then, for example, if they should satisfy 5 conditions, then the subset of the moduli space of all curves satisfying condition 1 is hopefully a closed subset. The ones satisfying condition 2 is a closed subset, and so on. And what you actually want to count is just how many intersection points do these different subsets have. And then in the ideal case, you can use intersection theory to actually calculate this. Just as we saw that in Bézout's theorem, the number of intersection points was just a very simple formula in terms of the degrees of these curves. And then so this was a basic example of counting curves on algebraic variety, but there's many more general geometric objects that you could try to count. So, and there's various connections between all of these things. And I would say in this picture, it's justified that the sheaf cohomology is at the center, because all of these things in one way or another will relate back to this. So it's a very important technical concept. But since we didn't have time to study any of the interesting applications, we didn't really cover it here. So this was all fancy drawing diagrams and saying how things relate to each other. But like in practical terms, if you actually want to continue studying algebraic geometry, what can you do next? So here, practically speaking, my advice would be first, since you already made it through so much of Gutmann's really excellent script, what you can do is in your own time, just finish reading that script. Because, I mean, what is now introduced in the last part that we didn't cover is exactly the sheaf cohomology, which is kind of important. And now you already learned all the language that Gutmann prepared. So if you intend to continue to these applications, then it makes sense to finish up learning about this concept. And then if you want to continue, what I can really recommend as a source is this script by Vakil called The Rising Sea: Foundations of Algebraic Geometry that we already referenced in several parts. Because so this is how I personally really learned algebraic geometry. And what I like is that this script takes more time to, for example, study examples, to fill in details of various arguments, to prove all those little lemmas that you need to really navigate theory. So in Gutmann's script, the feeling is really that Gutmann chose some key points to reach, like for example this 27 lines on a cubic surface, and then found basically the optimal way through the theory to get exactly there. But this means that the path is kind of very directed, pretty straight to the target. But you don't learn so much of the surrounding theory. So if you really want to learn about other concepts, learn about these more general applications, then it makes sense to take a bit more time to get familiar with all the different theories, do a lot of exercises, example computations. And Vakil is really good at this, at giving some intuition and also giving you all the tools that you need to continue in the study. So if you want my advice, this is a really, even though it's a very long book, it's also a really great book to learn this also by yourself, if you want. Okay, this is now really everything that I want to say. Thanks for sticking to it until the end. I wish all of you a great summer vacation and a good preparation for the exam if you want to take it. Okay, so see you then.